Okay, my name is still Glen Meyerowitz, and I'm still working on using embedded sensors to recognize weather patterns that can degrade autonomous vehicle performance. So I'm going to start off giving a little bit more background about what are autonomous vehicles and what are different levels of driving automation. So this might be something that some of you are familiar with. So a few years ago, the Society of Automotive Engineers, SAE, came out with this chart to describe the different levels of automation from level 0, which is no automation. So that is a fully human-driven, 1980 Corolla, to level 5, which is something that doesn't exist yet. That's the idea for future full, the golden ticket of a full self-driving vehicle. There's kind of this distinction that exists here in between level 2 and level 3. So 0, 1, and 2, the idea is it's human controlled, and then the autonomous system is there as a backup. For levels 3, 4, and 5, you can think of it as the reverse. So the autonomous system should be in control, and then really the human is there as the backup in case something goes wrong. For a lot of what we're going to be looking at now, I'm going to be focusing on level 4. And so level 4 is a system where it's supposed to operate by itself within a specific operational design domain. And so what that means is that there's some constraint that's created by the developers, and then within that domain, the system can be fully autonomous. And when it's outside of that domain, the human has to engage and be in control. So this domain can be based on a variety of different factors. It could be location-based, so that's called geofence. So for instance, when you're within a parking lot, you can be autonomous. It can be geography-based. So that could mean when we're on flat ground, we can be autonomous. But if it's slopes above or above a certain grade, then we cannot be. Time of day, so it could only be from 9 a.m. to 5 p.m. Weather, so you could say we can operate in sunny conditions, but we cannot operate in rain or snow, or other conditions that you can think of. And typically your ODD is based on a desire to avoid certain types of environments. So snow is a big one, right? It's very different to operate in Miami versus to operate in Chicago or something like that. And so this decision of operational design domains leads us to the real question for autonomous vehicles is not when they will be deployed, but where they will be deployed. And so this is often a question about unit economics of where is there a business case where you can make money with an autonomous vehicle, and it's also simple enough for your vehicle to operate there safely. So this leads us to the question of what is the impact of varying weather conditions on autonomous vehicles. So what really is an autonomous vehicle, right? So it's going to use a suite of sensors to perceive the world around it. Those sensors will feed data into some kind of central processor, which will determine the state of the world based on that sensor data and its knowledge of the world, right? So the state at T0 and then kind of all states before that. And then as ambient weather conditions change, of course, it's possible that the sensors on the vehicle will behave differently, right? So they could experience degradations or failures. So if you start off leaving in the morning and it's sunny and then it starts raining, you can envision that cameras and other sensors might begin to behave differently, which could impact how they perceive the world and the data that they give you. So when we ask the question, what's the impact of weather on autonomous vehicles, this in many ways really boils down to the question of what's the impact of varying weather conditions actually on these sensors. And so here I have a list of a few different sensors: camera, infrared, LiDAR, radar, ultrasonic, GPS. Obviously there's more sensors, and then a variety of weather conditions: rain, snow, dust, fog, glare, darkness. I guess maybe weather conditions might not be the right word, but varying ambient conditions. And then here's a high-level chart kind of how some of these conditions can impact these sensors. Important to note, this is really just to kind of a first order. As the severity of any weather condition changes, it can have a very different impact on the sensor. If it's a very light rain, that'll have a very different impact than a very heavy rain. And so you can see that a lot of the sensors, particularly speaking of cameras, will have a lot of degradation as soon as the ambient weather changes from sunny and really nice weather. So what is the impact of changing weather conditions on human drivers? So how do we change our own behavior in different weather conditions? And so as I'm sure anyone here who drives knows, when the weather changes, you should, and you often do, change how you drive. So here's a chart that shows as the speed limit increases, when weather conditions get worse, there is a larger increase in how fast people drive from clear weather conditions. So you go 5 to 10 kilometers per hour slower when it's wet or at night than you would if it was clear in the middle of the day. And so this is not only because of how how you perceive the world changes, right? So what you can see is physically different, but of course also the physics of how the vehicle interacts with the world is different, right? So from hydroplaning or skating on ice, the interactions between tires and the ground will be different if it's wet or icy. So what do autonomous vehicles do now? I guess I want to start off by saying, obviously there are dozens at least of companies that are developing autonomous vehicles. Each one has their own path forward, and that's constantly in flux. But to the best of my knowledge, there's currently no consideration for changing ambient weather conditions on how autonomous vehicles operate. So the vehicles have a given set of parameters, and so these can be based on things such as a high definition map or something else that determines a state function. And that will control things such as what's the maximum speed you're going to take on a road, what could be a turning radius that you feel comfortable taking at a given speed, what's the following distance between you and the car in front of you. But these are not parameters that change as the external state of the vehicle changes, because that's a very difficult problem to solve. And often by carefully controlling the ODD, you don't need to do that initially. So that leads to what am I looking to do on this project. So this is what I discussed last time. So to create a label dataset, database of images that show a range of different weather conditions that a car or vehicle may experience on the road, train a neural network to identify and classify the images and video based on the weather conditions, deploy that to a small embedded device that can use a camera to emulate one of these autonomous vehicles, ideally create a way to vary weather conditions in a custom environment, and then assure that the system properly adjusts some kind of finite state machine to account for changes in these external weather conditions. So what are we looking to do technically? So this is an implementation of VGG16, which is a well-known and used convolutional neural network for image recognition. The only, I guess not the only downside, but one of the downsides is very big, so it takes a while to train and then to do inference on. But so you take your images, scale it to 224 by 224 by 3, and then you run it through these series of 16 convolutional layers. I'm implementing it in Keras on top of TensorFlow. The data set that I have now is about 1,300 images of dark conditions, rain, snow, and dust. And then one thing to look at, right, is how are you going to predict the label for a given frame? So this is, of course, something we were actually just discussing in the last lecture because for my model, it's trained on individual images. Is there a way where you can get a higher accuracy on a prediction of a video than you would potentially on individual images? And so you can use a fusion scheme to more accurately predict what the label for a video is. So I'm using classifier fusion based on this. So we'll just take the average of the past n number of frames, where n is going to be whatever hyperparameter we have, and then we will just do the argmax of those labels to figure out what do we want this, the label in this frame to be. Of course, that does run into an issue where when you first start, you don't have that historical data, so you might not be as accurate at the beginning, which of course can then impact your accuracy down the line, but what can you do? Data set for ambient road conditions. So here are the 4 categories that I have. Rain, snow, dust, night. These are I got from skimming images from Google Images and just downloading as many as I could. I guess not as many as I could, but as many as I reasonably wanted to. Spent some time determining the optimal learning rate. And so I'm looking for my training, I use between 10 to the negative 5th and 10 to the negative 3rd. If you go beyond 10 to the negative 3rd, then you are most likely going to overfit your data. So the training results that I have right now, I'm still only getting about 80% accuracy, which is less than where I want to be. And so that's something that I think I need to spend a little more time going through and pruning some of the images that I got from Google Images, because I'm sure some of them are not correct, which is unfortunate. It takes about 60 hours to train. It's got about 50 epochs on my laptop. So like I've only been able to go through it 3 times. So I'm hoping to get one more training session in for.
Well, why don't you use the Google Colab?
I guess I'm just not as familiar with that.
Okay.
So yeah.
Or you get free GPU.
Well, I'll get that started. We'll see. Yeah. So on my laptop, it takes quite a while, which is not great. Remaining milestones is to achieve a higher accuracy. So I'm looking to prune the data set a little bit more. Just this past weekend, as anyone who's here knows, it was raining, which is unpleasant. But I actually got to record some good real world data in my car. And I'm looking to deploy that on the Jetson Nano for real-time inferencing. One thing to note as well, when I do the inferencing on my laptop right now, very much not real-time. Yeah, it takes a little bit under a second per frame, so not real-time. One interesting weakness of this, which is the last thing that I'll discuss, is the fact that anything really that's neural network based is prone to adversarial attacks. And so there's a pretty cool paper and video that came out by the team at Tencent Labs, where they practice doing adversarial attacks on Tesla, on a Tesla car. So Tesla is the only company that I'm aware of that uses cameras for any kind of weather detection, and they just have something called Auto Wiper, where they have a camera on the front dash, and if it sees what it determines to be water, it will turn the windshield wipers on. So it's not used to adjust any kind of finite state machine into the vehicle to adjust behavior. But they were actually able to literally display this screen to what any of us is nothing. And that is capable of tricking the camera to think that it's rain. And so that's just, because of how the neural network works on the camera, just and how it's trained. So obviously there are adversarial attacks that are possible as soon as we add automation to vehicles. So, sensor fusion, combining multiple modes is kind of the best way to avoid that. If you're only based on cameras, then that's a little harder to do. Disclaimer, anything that I've said only represents my views, FYI. References, any questions?
Yeah, so how big was your data set for training of those four scenarios?
Yeah, so I have 1,300 images total, give or take. So that's divided, give or take, evenly between those. Yep.
Is your testing data set also like from those images? Or
yeah, so I guess it's 1,300 images that I then divided about 70% to training and 30% into, or I guess split between a validation and test, yeah.
And then, like when you're training it on VGG, are you just like changing the last few images? Because like if you do it that way, it could probably like take less time than $60. So you can just like use a pre-trained model and just transfer learning on that. It might help you.
Yeah.
I'm not sure.
Yeah.
You could actually like break it down to.
We can chat more offline, yeah. But yeah, I'm not retraining the entire thing. So I am using a pre-trained network. But then I guess, I'll have to take a look back and see how much am I retraining. I don't know off the top of my head. I have to look at my code.
How do you calculate that? Is it like using cross-validation or use some data set that's trained on some last?
Yeah, so I just downloaded a large number of images from Google, and then that's split between all the different sets. So it's on that.
So do you have a separate validating test and a separate test set? Because it sounds like you have already tested, and now you're going to iterate on it, so it's no longer a test set. So the way you should do it is your test set should be done once at the end. Okay.
Yeah.
Validation training and validation, and that you do by whatever and cross validation. No, and you optimize everything. Sounds like right now you have used all your 1,300 images, so now you're going to be iterating on it. So your test set is solid. Test should be done on something just once, exactly once, and that. Yeah.
So what I'm looking to do for the final test is going to be either data that I recorded this past weekend from my car or from a small. If I have time to. So it'd be a fresh set for the real test. Yes.
Okay.
Yeah.
Can add some feedback because the system will send a different command to vehicle. Depends on different weather, right? But,
correct.
How can we clarify that the command is suitable for that weather?
So the idea is that you'd have some kind of state function in the vehicle, and then that state function would determine some wider parameters of how the vehicle operates. And so let's just take maximum speed. So normally your maximum speed for your vehicle is maybe 60 miles an hour. And then if you determine now it's raining, then you can drop it to say 50 miles an hour. Or if it's snowing, you could say, okay, now we're only going to go 40 miles an hour or something. So you'd have a way of altering certain parameters. So it's not necessarily that you'd like that would control the, that like if you say it's raining, like that wouldn't control the vehicle itself, but that could be used to kind of choose parameters of how the vehicle operates.
That's cool. Okay, let's move on.
Yeah.
Could you move to the next slide?